Okay, so good morning. I will start today with a continue with the functioning group on the stable definition. So recall something I didn't say before, that the Cuntz semigroup defines function from system algebras with star morphisms to, let's say, form that is positively ordered monoids, right? And well, as a functor, as Frances showed, the Cuntz semigroup exceeded some more information than key theory. But if you wanted to replace key theory by Cuntz functor, there is an advantage for key theory. It has that the functor is continuous, meaning that K0 limit of C-star algebras is the limit of K0 of AN, that's an inductive limit, and well, K0 or K1. So this is a nice property because many constructions with C-star algebra are done using inductive limits. But if one tries to see this for the Cuntz semigroup, let's see what happens. So let's see a couple of examples. Complex numbers and start building the one build the compact operators. Closure of these things. Anyone thinks the functor W. Recall that the Cuntz semigroup of matrices was given by rank. So this is natural numbers, since these elements are included here, preserving rank, and these maps are continued. Right, so if you apply the Cuntz semigroup functor, then naturally, if one, well, this, let me see. This is a limit in the category of C-star algebras. See, okay, and well, if all these are identities, whichever it is the limit of natural numbers and identity, right? But in here, you have matrices with infinite rank, so this is not going to be right. So you can see that one semigroup of the compact operators is actually natural numbers together with infinity. So now with this one, if we consider another example, now a unital one, it's complex numbers, you put this, right? I'll repeat the car algebra. Frances has already written what is the Kuhn semigroup of this, but let me. And so on. Take the inductive limit is m go to the n. M to infinity. This is the car algebra. Now, if you these maps, sorry, say we're taking to be diagonal inclusions. So if one builds the Kuhn semigroup again, actually the natural numbers, but these maps are now units of the weight. So since this is multiplying by 2 the rank, then probably it's a nice thing to write inclusions this way, right? This would be Kuhn semigroup. This again goes to 4 and so on. And this inductive limit in here in positive order monoids. This is only it's actually the union. Right? This is, let's write this union. The added positive integers. But this the Kuhn semigroup. So well, it's easy to see that in this sister algebra, one can, yes, it's recording. In this sister algebra, it's easy to produce infinite common projections pi, let's say. And so in the algebra, right, without going to matrices. So say A to be the sum of 1 over 2 to the I is pi. Then 0, the spectrum of A is easily seen to be isolated. So one can see that A is not, well, as Frances showed, A is not equivalent to B projection. And note that all these are projections. Okay, this well, one has different ways of saying that this is not going to be the Kuhn semigroup. So this is different from which is, let's say, the limit as positively ordered monoids of 1 to the end. This with these inclusions. Okay. Okay. So one way to remedy this was introduced by Coward, Elliott, and Ivanescu, defining a stabilized definition of the Kuhn semigroup. which is why I know. Which this tool in 2008, given A is the algebra and define A to B. So now you don't simply take infinity matrices, but you get the stabilization, which is now a C-star algebra, take positive elements and model of Cuntz equivalence. Okay, and in here you define an order as before. And an addition. Oops. And since now you don't have finite matrices, you need to, let's say, fix the isomorphism. Okay, you fix an isomorphism of this is, since you're stabilizing here, so this is isomorphic to 2 by 2 matrices. So there's a way to define this through gray image of this, or let's say the image here. So fixing an isomorphism, you have a new definition of the Cuntz semigroup, which is hopefully more well behaved, and we'll try to solve this problem. How is this going to work? Now, note that in case one, both CU of so in this case, when you compute the Cuntz semigroup, you already get this. Oh, okay, probably right. Let's see that this and much of course, so that will be infinity. So that's not much. So this is going to work, but in 2. If you try to look at this thing, okay, so if you only introduce infinite elements, kind of doesn't seem to be adding much, right? Because probably you will be getting like so in each of these finite steps, you will be getting like this same thing with an infinite element, but this probably should be something like n to the 1/2 infinite. But this element we are building here, so this is letter equal 1. So it's not going to be this infinite. So still different from CU of n to infinity. Okay, what I wanted to go is that this is not so straightforward. What you have to do is also change the category. So what we'll see is that this semigroup with this addition has an additional order structure, which puts them in a different category in which inductive limits work different, not only like making these units, but making these units and then somehow completing. So what we will have is that goes from C-star algebras to positively ordered monoids. So this was not continuous, but now one defines CU to a new category, which is called CU semigroups, and now CU is continuous in the sense that it will preserve limits, as in this case. So once introduced in this way, there was a natural question of can one actually go from here to here as some way of completing monoids and getting these CU semigroups so that this thing commutes? And actually, you can still do that, but you have to somehow change in this functor, like enlarging this thing, say local C-star algebras. You have to also change the category in which you build the original Kuhn semigroup. That will have to define additional structure to the original Kuhn semigroup. Well, let's say we have some thing. Here is some W semigroups, and then this mark. And this is like this is a natural completion from local C-star algebras to C-star algebras given by completion. There is a completion from this category to this category. This is continuous. This is now continuous also with this range category and source category. And those things have some that name. Retractor, refunctor. ¿Entendió una yo? Reflector. Okay, so there are some reflector functors in here, which okay, no, so these are the reflectors. Sorry, the completions are reflectors to these maps, which are the natural inclusion from CU semigroups to W semigroups, or from C-star algebras to local C-star algebras. Okay, but for this, we'll have to do several things. First of all, what we'll do is study which is this category and see that this semigroup actually belongs to this category. So, and go on to that. Well, the category CU. First, let me define what is compact containment, or the way below. That's a definition given this is any ordered structure. That set, as I said, with a pre-ordered relation. Take two elements, we say that, and that's going to be long to write. A is sequentially way below or we should say B, so sequentially way below or sequentially compactly contained in B if whenever A is less weak, if A is less or equal to B, and whenever B is covered by supreme of C sub n, where C sub n increasing sequence. It is n0 that the less or equal C sub 0. Okay, so that's the definition of being way below or being compactly contained. That's I write them both because I will probably use both names. The sequentially not going to use it again, but this is this has to be stressed because this definition implies some numerability here, so contability. The fact that this is only an increasing sequences, it's not any directed set. It has to be a sequence that that in some places marks a difference. So the thing is, an element is way below or compactly contain another if you can cover this element with supreme of some others, then at some finite stage you will be covering this A. So that's somehow an idea of what a compact thing is, not something that you can cover when you have any cover for a compact set, and you have a compact, you have a finite subcover, right? Where am I? These those are all Cuntz semigroups, but if take S to be 0, the interval 0 infinite with ordering, then A will be below B, even only if A is strictly less than B, or one can see that being strictly below, not being infinite, well, no, being some strictly below already implies that this will happen. And if A equals B equals 0, this is also true. Another, if you take it has to be integers together with infinite, also with another ordering, then A only if A less or equal B and A cannot be infinite, right? I think these are the. So compact containment is so you have a lot of compact. Everything is compact in here except the infinity, and it's compact. I didn't see that. Everything is compactly contained in itself except the infinity. Okay, let me get the last example. It's x locally compact. Also space, and let's make it single. Compact, that is, all elements are countable union of compact subsets. And take S the open subsets, then one clearly says that one U is way below with order. And conclusion. Then U is way below P. Sorry. If and only if there is K compact such that U okay, and to see this, I'm not gonna take much thing, but this is clear. This should be clear, no? If you have a compact set and then you cover V as a if you can cover this B with a union of open sets, and this gives you a cover of K, which will have a finite subcover, and that will give you the finite stage that you want. Right? So this should be clear, and this direction is also easy by sigma compacity. You write V as a union of K n and what? And that means that U is way below V, which, well, you can make this increasing. So this is N such that well, and since this is a union, B is a union of these things, this will also be below here. Okay. Well, what I wanted to do here is stress the fact that one thing that you use is getting an element and writing it as a supremum of some things which are, in this case, they are compact, but we are somehow increasing with this relation. This will be a particular property of Cuntz semigroups. Okay, so once having this defined, find the category CU. following order conditions. So I'll list now a series of conditions in an ordered So let's say I have an ordered monoid S. That means it has an addition with a zero element and an ordered relation, which is compatible with addition. This is positively ordered. All elements are positive. This I'm not saying. Positively ordered monoid. These conditions are usually called axioms. They call it axioms O1. The O stands for order, probably, and they always go for these names. S is closed by suprema of increasing sequences. That's axiom O1. O2 says that for all S, there exists an increasing with that. So all elements can be written as suprema of this will be called the rapidly increasing sequence. This is axiom O2. Then O3 says this is a compatibility relation regarding compact containment and addition. If S1 will be T1, S2, T1, S1 plus S2 is way below T1 plus T2. Note that this compact containment compatible with addition is not the same as saying that compact containment is preserved by, is preserved by translation. This is not necessarily true. Okay, so not that this relation is compatible with addition in the sense that you can add and this is preserved. This usually will not happen. Right. So what I want to say is that this is not necessarily a condition that's happening. And finally, for it's also compatibility of suprema addition if using sequences, then supreme of equals supreme. Okay, so this will be CU semigroup. Satisfying for is then okay, so some CU semigroup will be possibly the other, right? Satisfying all these four conditions. Um, and PSM is um, for that preserves complement and supreme. So any map that preserves supreme and compact containment, addition, the other relation, and zero will be CU morphism. Now, like CU degree CU semigroups with CU morphisms. Theorem now. Again, forward. If A is an algebra U of A is, well, CU of A with the order and addition defined is a CU semigroup. And tutorial. Probably I have to say. Let's make this I'm going to do this tutorial with a natural way to define morphism, right? We have a star morphism in here. It will go to CU morphisms. Moreover, well, yeah. Limits and okay, so we have a category in which to define the Kuhn semigroup. What I'll do now is to prove this, that CUA is actually CU semigroup, and it satisfies all these ordered relations, and that the category has inductive limits. This would be in another session, which would, this will be provided by Laurent. Much. Yeah, shouldn't fail. Okay. Before going on, I mean, I'm not going. This is going to be proved in several steps. Only let me recall that the motivation for these ordered things or how this will go is that if we have A in that positive element in here, we will have, this is clear, that any element will be written as a supremum of these cut downs, and these things will typically be elements way below. So cut downs will give us the idea of being an element way below another. So this is what we have used to prove a 1, 2, 4 in CU of A. Okay, so well, I'll just start. Before giving a proof, let us have some observations. Regarding Kuntz comparison in the stabilized indeed. So what's the advantage of going all the way up here to make a comparison? Recall this has only been stated, but if A has stable rank 1, this was shown by Francesc, that means A all elements can be approximated by invertibles, or in the non-unital case, the unitization can be approximated by elements. Right, so this is an element C-star algebra has stable rank 1 whenever you can approximate all elements by invertibles, or elements in the unitization by invertibles. Then comparison. We have two elements. A function if and only if for all epsilon there exists a unitary such that okay, so there was a way to implement Cuntz comparison using unitaries. This is very useful in many computations, that you can use unitaries to move cut down from A inside the hereditary algebra of B. Also, this you will be able to do this for this inside the hereditary algebra of any cut down of B, any some particular cut downs of B. And it turns out this one needs to approximate A. That is, in here, you don't need to get in the non-unital case, you don't need to get all elements of A, but you need the all elements in the unitization, but all elements in A is enough. So that this condition is enough. So this was not there was not a proof for this in the course, but if one goes to the proof, which is not that long, but it involves forward conversations and so on, one sees that one only needs to make this approximation. So this is something called usually weak stable one. So when one has this condition, then one can also characterize Cuntz comparison with these unitaries. And now suppose has stable rank 1. Okay, let us see that the stabilization has weak stable rank 1. So what we could, when making Cuntz comparison in here, we can use this this result. So on that first, okay. This is what else? This is here. So if you have x in A and so and n and A, then x as A times B. One can write x as a product of two elements. This using the polar decomposition. Write x as B times x. So this is A times x to the 1/2. This is A, and this this lives in the simple algebra for 7. And this also. Well, sorry, where? You write x as a product of two elements, and hence x is lucky. So then you write x. So by going up to n matrices, which is still inside the stabilization, note that all these couple elements are all important. And then is important, then lambda plus z is invertible. For all lambda different from 0. Okay, so if you have an invertible element, this is in the unitization now. Okay, so this is in the if z is in here, this will be in the unitization of the stabilization, or even M2n. So you can approximate this by invertible elements. You can approximate this by invertible elements. Products of invertible elements are naturally invertible. So x sorry, that is approximated by sending lambda to 0. And so if finite matrices can be approximated by invertible, then so can every element here. So K, this is contained in as desired. Weak, stable. Okay, and probably, yeah, probably this is this is a place to stop. We'll continue then proving 01 to 04 for Kuntz semigroup. in that. Okay. So let's make a break. All right. Now let's see one satisfies 1, 2, 4, and so I'll start by 1. That is by increasing sequences. So suppose we have we have x1, so x1 CU of A, then there exists AI in B, and so on. So there exist positive elements such that I equals the conjugate valence of this AI, and so we have an increasing sequence of conjugate valence. Let us fit some notation that will allow us to consider these sequences in these increasing sequences in increasing level of generality. So I'll give you, this is not a real notation, but that will be part of maybe I will try. Part of the cases that we will consider a case in which this is simply increasing, A rather equal B, and then A, we'll say A contained in B if A is in the hereditary algebra generated by B. Okay, and A, if there exists U if there exists a unitary such that U A U star is in the hereditary algebra generated by B. Okay, so note that all these conditions all imply A subequivalent to B, and they're increasingly general, right? So let's consider some cases. Case 1, suppose we have and moreover the limit exists. So should have even key to be the stimulation. So we have, but that will be positive, right? If all these elements are already positive. So we have a positive element, which is the limit of these sequences. Then in this case, clearly we have a n, so the limit will be for everything. So all elements will be less or equal this. So this will be given for a algebra for a xi's. So suppose B any epsilon greater than 0, since this is the limit of these things, there exists an n such that so this can be arbitrarily close to here, and this implies that a minus epsilon plus is superequivalent to an, which if this is any other upper bound, this will be superequivalent to b, and this is for all epsilon. So if a minus epsilon is equivalent to b for all epsilon, is implies that a is equivalent to b. Okay, so a is the last upper bound. Is this element with x n? Okay, so this case works well. The case 2, suppose we have one so suppose we have an increasing sequence in this sense. A1 is in the hereditary algebra generated by A2, A2 in the hereditary algebra generated by A3, and so on. Then let B n to be the sum once 1 to n of a divided by um, times 2 to the I. So this is not, well, this has I mean, that's going to be simple. Well, they are all different from zero, okay? So that doesn't make any problem. Well, we write this because we can then write b equals sum of 0 to infinity of the same thing. But now the normal field is bounded, so this is actually here. And clearly the BNs and this, if you take these elements, these BNs are increasing, but also note that since AI should have been that before. Let me try this again. AI is equivalent to this element is equivalent to a scalar multiple of this thing, which is less or equal to 9. Therefore, it's function bi. On each of these bi's, this is clearly in the hereditary algebra generated by all the i's. Well, didn't use this notation before, but that means the hereditary algebra is generated by these elements. And since they are all contained in each other, the hereditary algebra generated by AI. So that means that it's to AI. Therefore, AI is conjugate to BI, right? So these classes are equivalent to. So these BIs are equivalent to the same things. Therefore, B index, which is the supreme, which is B. Okay, so by case one, here it is. This B. Let's make another case 3. Because this doesn't change that much. If we have so we're going increasing generality. So now we have this, but you have to add you have to conjugate by unitary to obtain the hereditariness. But now let's E1 equals 1. Supposedly, it's in the hereditary algebra of A1. Yes. Mm. Where these PIs, then we have given each of these, since it's given by conjugating by unitaries, this is equivalent to A1, to A3, and the result follows by no, I'm not sure if I'm doing it right.
Should it be e sub I up to this one A1?
Sorry?
E sub I, e sub I minus 1 to A1. You want A1, you want start. You always start with A1, isn't it? I believe.
You take, I will change this one, so it seems contain. So isn't it true that probably I have to change the style? Sorry for that.
You have to take U1 star and the other ones with stars, and at the right.
Yeah, because what I will do is that instead of saying that you put this inside the hereditary algebra, this one, then by conjugated by UIs on the other side, you get this inside the hereditary algebra conjugated. Isn't that the thing? That implies that AI is the hereditary algebra. You start AI plus 1 U I. So well, let me leave it this way, and if not, I have to recheck it But you actually like, I mean, you cannot continue changing this one, so you can change this one, so then change this one, and change this one, and so on. So you have to make this be inside the hereditary algebra of the following one. Okay. And now case 4. Since for case 4, let me write what the general case is. We have okay, so since this has weak stable rank 1, then it's going to be. This is a combination of this weak stable rank 1 condition and the Rodham's condition, even though if for all epsilon there exists delta and unitary in so if we have weak stable rank 1, then Cuntz comparison reduces to seeing that for all epsilon there exists a delta and the unitary such that a minus epsilon plus is well, let me not write this since we have a notation. Okay, so we claim that we can write, I claim that we can choose epsilon and such that what? Such that a n minus epsilon was is Cuntz, well, Cuntz okay, graphically you will see what I mean. Okay. Okay, so we can choose epsilon positive elements converging to 0 for all n in such a way that these sequences are, I don't know, we didn't give a name for this, but containing the hereditary algebra of this after conjugating by a unitary. To this end, what we do is you start by doing this in here. This is nothing to do here. You just choose any sequence that goes to 0. So this epsilon. Okay, so this converges correctly here. Now, using this weak stable rank 1 condition, for since this E1 is conjugate equivalent to E2, then for each epsilon 1, there will be a delta, and epsilon 2, epsilon 1, 2, for which you can put it here. Okay, so this is a A2 minus epsilon 2, and so on. Okay, now you will continue going up. Just making clear that the next one will have to be smaller than epsilon 1, 2. You can always do it, and just ensuring that the sequence converges to 0. You will always also be capable of doing it. Then A2, minus epsilon 2, 2, and so on. Okay, so, and then you will have this, still going in this direction, minus epsilon 3, 3, and epsilon 3 plus okay, so we will be able to choose the sequences going to 0 in that way, and then like here to be the diagonal ones. Okay, so we will try to follow the diagonal, and the diagonal goes here. A and minus epsilon in plus you choose these elements, and these are clearly suitable to be to an, right? So each of these elements will be suitable to your an. What we have now. The n. This is so it's going diagonally. This element is u below this one, and then this one. Okay, so in particular, this will be if this is in the hereditary algebra of this one, this is below this one, and this is after composing with you in the hereditary algebra of this one. So U1, it's all this as premium B bar case whatever, bar case 3. Also, each ends equals the supremum. Okay. A minus epsilon. So each of these ends are written as the supremum of this sequence going up, and this is less or equal the supremum for all ends of an minus epsilon n. So to see that this is true, that this supremum is less or equal than this one, for each of these elements, note that if we are below the diagonal, you can go to the diagonal following this, and then this is going below the next one. And if you are above the diagonal, you can go to the diagonal following these horizontal things, which are all used, so it's going to be low, right? So this will be clear, and these are the BNs. So B is actually an upper bound of all the ANs. Now, if Q is upper bound, sorry. Well, no, this n is fixed. This is not. Let's say. Well, so my name. Sorry. This is the supremum, and then go to this general supremum. I have to forget about m's and k's in here. So this is true for all n, and then this is an upper bound. If you have another upper bound, then well, for all n, you have the bn. No? So we have that the bn's are less or equal, are subequivalent to an's, which will be subequivalent to C, which implies that the sup of the PNs would be below C. So this would be the supreme of the sequence. And we write B. Observe. and with B. So that this will be something that we'll be able to do in general when we are looking for a suprema of an increasing sequence of the AIs. We can choose representatives which are actually increasing and converge to a representative of the supremum. And this sequence will be things which are below our original sequence. You cannot manage in general to get it equivalent, but that will be enough for what we'll need. Okay, so this is an observation that we'll use in future things. Okay, so okay, so to prove O2 given A in C of A, I will write that A is the supremum of AN. So this is what we have to prove. By case one, it is clear that A is the supremum. Let's see, A minus 1 of plus, so this is an increasing sequence that converges to this, and so we only need that in general. Probably the same in A. Okay, because any successive cut downs, one will be a cut down of the previous one. So we will be way below. So suppose we have that A is less or equal let us say that this is true. Suppose that this A is less or equal to a supremum Bn for some well, by the observation, we can choose Cn's what equals to Bn and it's increasing and that is so we can choose an increasing sequence and these elements. Now, since A is less or equal C, A C, that implies that there exists, note that epsilon is already fixed. So there exists delta such that minus epsilon plus is equivalent to C minus delta plus. Now, C is a limit of the delta n's. That implies that there exists some n such that norm of C minus Cn is less or equal than. This implies that C minus delta plus is equivalent to the Cn. Cn, yeah, it's n0, so n0. So this will be equivalent to Cn0, which will be equivalent to Dn0. That implies that A minus plus is less or equal to N0. Okay, so that's for if you cover A by a suprema, then at a finite state you will be above these things. That's the definition of this. We being way below this one. That will go through before, but just let me observe one. Actually, build some A epsilon. Well, yeah. Oh, no. Let me not say that. Sorry. Well, all three, that's a technical thing. Suppose we have E prime is way below B for some E prime A and B. This is a particularity of stable algebras. But you can choose orthogonal representatives easily, or we'll go to matrices, and we can assume A prime, orthogonal to B prime, and orthogonal to B. So there will be by O2, there will exist epsilon greater than 0, such that A prime minus epsilon is so such that A prime is subequivalent to A minus epsilon plus and B prime is subequivalent to B minus epsilon plus. But if these two things are are orthogonal, then this is equivalent to a minus epsilon plus, which is a a plus b minus epsilon plus, which this is well, if these are orthogonal, this is the same as a plus b minus epsilon plus. So, and these would be the same as if these things are orthogonal, then this is the exact same sum. But this is already way below, so we want to. Sorry, this is way below. This I never say, but one can check. This is an auxiliary relation, meaning that if you have compact containment and then a superquality, this implies that this is compactly contained in this. Okay. And well, shall we? Riemann condition. So let's say you have two sequences. One of the inclusions is clear. It is clear that the supremum is because all these elements are bounded by, this is bounded by the supremum of this thing, this is bounded by the supremum of this thing, then all of these will be bounded by the sum. So suppose we have two sequences. Choose n prime and prime. Choose increasing sequences as in the observation, and how does that go? Then for the other one, supreme that would be what? Let's say this converges to A and this to element B. And well, now once written as a matrix, this is really the supremum Okay, for these sequences, you can write it as okay, because this will also be increasing and with the same thing as a limit, which is equivalent of the supremum. So each of these ones will be equivalent to the supremum of the prime prime, which is superequivalent to the supremum. Each of these is equals. So suprema is preserved. Okay, and well, I still wanted to prove that that the assignment is functorial, but I think I won't have time. But it's not. I mean, to see that it's functorial now. To see that it preserves suprema will be again using this observation. To see that it preserves compact containment, one will have to use this characterization to prove with the fact that star morphisms will take cutdowns to somehow cutdowns of the elements. The thing goes on. Okay, so part of the theorem proof that U of A is same. Okay, so still have to prove that the category has limits and that the thing is continuous. But we'll see you next day.